Okay, just checking.
Oh, sorry for the first line. For the first one, the link. You know that my topic is linking, finding the linking between fault damage zone mechanical and geometrical characteristic with fault seismic history. As I said before, the concept that we are going to use to find this relationship between seismic history, fault segmentation, and associated damage zone is structural maturity. For that, I just going to this. No, I should change it to this one. Yeah. As I said, we start with fault segmentation, and for that, at first we prepared a very precise fault trace of the Rocabretoro fault. We start with Rocabretoro fault, and I presented before. And then for segmentation, as I said, this is very important that we find the distribution of cumulative displacement along the fault. As I presented before, we tried 3 attempts to determine this distribution, and we didn't found good results. So this is the new method that I'm trying to use it for Rocabretoro fault, and it seems we have a good result. And I just make a very precise profile along the facets, and in the area that we can see the changing in the slope, like here, we consider it at the top of the facets, and the vertical distance between this point as a top of the facets, and here that is 0, 0 as a contact between this profile and the fault trace. We consider it as a through, the midterm through. And if we can find some places like here that there is another changing in the slope, we consider it as a short-term displacement. And for example, you can see it for this facet that is here. The midterm through is 225, and the short term is 70 meter. And just I can finish this part, and then I wrote a code in MATLAB to project that cross between profile and fault trace, projected on the line that we can choose it in every direction. And this is the result for this part for cumulative displacement for midterm and short term. And this is soon that we make a conclusion for that, but it seems that we can see if, for example, we consider it here as a segmentation, that we have a very deep drainage here, incised drainage here. We can see that the cumulative displacement goes up and down in this part, and again goes up and down, but it's very soon to calculate. I should finish all of them, but this is the last attempt for determining the cumulative displacement. On another parameter to determine the structural maturity, we need the seismic history. For that, we on June. Okay, I have problem. Oh, yeah. In June, we opened 2 trenches on the antithetic part of the fault trace. Here you can see the trench 1 and 2. There is about 250 distance between them. And this is another trenches that Lucilla and others opened it before I started my project, but I'm going to use the results for in this project in my PhD project. And so we had 2 walls for each trenches, and I make a log for each wall. You can see here the trench, the wall, southeastern wall of trench 1. Here with this with log you can see it better. I distinguished 7 sedimentary units on trench on the wall on the log, and I considered 4 event horizon, 1 event and 4 event horizon here. You can see the most recent event is here because of this offset, and I put another event horizon at the bottom of this collovium wedge, another one at the bottom of this collovium wedge, and another one at this bottom of this collovium wedge, and another one here. But there is a question about this because we can see this offset, but this is necessary that I do the restoration for this log to make sure maybe with these events we can find this displacement, absorb this, actually restruct this displacement, and maybe this is very large offsets. Maybe it's because of the clay that we have on these both actually these 3 units, and maybe this large offset is because of that. But as I said, we considered 4 events, and we took 13 radiocarbon dating sample from this wall. Fortunately, 6 charcoal and 5 bulk, and I just prepared them to send them to the lab for dating. And this is another wall, again in trench 1 in northwestern wall. You can see the log. I just try to correlate the layer in because as I said, the trenches are very close to each other. So it's supposed to we should find the same units in them. In the different trenches, and so I just based on color, they are similar to each other. They are correlated to each other. And again here, I considered 7 sedimentary units and 4 event horizon. One of them is here, the most recent, again for this because of this offsets, and I put another one in here at the bottom of this collovium wedge, another one here at the bottom of this. And for these 2 event horizon, there was another challenges, and we discussed about that a lot in on the field, and after that, because it's a very interesting structure here, and it seems that is because of the erosion of material on the scarps. If we consider them. We considered the position at the same time, we should put just 1 event horizon, and if we consider them in the different time, we should put 2 event horizons. So we should just wait for dating to make sure about the event horizon on this wall. I forgot to say that I put the place of the sampling here. You can see the charcoal with small cycle, and with and for bulk, for example, here it's maybe in these trenches is more with this curve for bulk sampling. And for trench 2 wall, southeastern wall, again we have 4 event horizon. One of them is here, one of them is at the bottom of this collovium wedge, and another one at the bottom of this collovium wedge. Because you can see the geometry of this layer, the blue one and the yellow one are the same. So we just put 1 event horizon at the bottom of this, and for green is because it's very continuously. So we didn't put another horizon at the bottom of this. It can't be a collovium wedge. And for another, the last wall, and you can see it, it was a little challenge. There was lots of challenge for this wall too, but because of that was very hard to separate the layer on these trenches in this wall. You can see it here, but this is the last version of my my log for this wall, and I just considered 3 events, and yeah, you can see one of them because of this color we considered as a colloquium wedge, and put one event here, event horizon here, and another one here, and another one at the bottom of blue, and the green is very continuously, so we ignore it. And it's interesting that we can find out, figure out the same event horizon in that about all of them, but actually in 3 first wall. And just this, we are waiting for the result of sample for dating to make sure about the interpretation of ourselves for the logs. And for the last parameter that we need, that is associated damage zone, I didn't start it because this is the part that I'm gonna to do it with Giulio and Michele in Padova. So I didn't start my secondment right now, but I had a short field work with Giulio, Michele, and Nolwenn as a Nolwenn PhD project, and just follow their survey and understand how I can do my survey on the field in terms of fault damage zone, and to can find the linkage between actually the segmentation and the fault damage zone and the seismic history. And right now, as I show you it at the first slides, sorry, here, yeah, here now, as I said, I need 3 parameters to figure out the linkage between segmentation, fault damage zone, and seismic history. Right now, I have the precise fault trace, and after I finish determining the cumulative displacement, I can make the segmentation better, and we have you can see we have a chlorine 36 sample here and here and here from the previous studies, and I have seismological study on this part and this part, and so this is a good distribute. And another trenches from Faculci and et al. Here, and so we have a good distribution of seismic history along the fault. And just I need to do the last part, is actually the fault damage zone to can make a better understanding about this linkage, the linkage between them. And thank you.
Okay, thank you, Nairi. Any questions? Anybody? Just put on your mic if you want to ask a question. I have one actually. For your when you were estimating your offset, so you distinguish 2 periods, so the short term and long term ones.
Yeah.
Okay, so what do they? I mean, why is there a change? So is that? I'm not sure I followed that. So the change in sleep rate, or yeah, is related to what exactly?
This slope?
Yes, a change in slope.
Yeah.
No, not this one, but when you look at you know, midterm to short term, so there's a change in of slope. Yeah, here. So it's on the left graph.
Yes. Yeah. Just we know that for facets we have a very smooth surface, and we consider it as a very smooth surface here. And if you look at the profile, M is here and M' is here, and this is the S for this profile, okay? And
Yes.
you can yes, and when we at the point that we can see the changes, this is the at the top of the facets, because this is the definition that you can see
No, I
the
understand that, but the question was more what is a change, yeah, in slip rate?
about the short term.
Yes, yes.
Yeah, it can be because of the more recent events, but because we don't have any document, we can consider it as a co-seismic displacement, but it can be because of the short-term displacement. So we consider it as a short-term. Yeah.
So you have dates for this period? I mean, related to the short-term displacement?
It's update?
Yeah, you have the dates for this period?
No, we don't have.
Okay.
Based on the reviews study, yeah, we know that the last event on this part is for one of them is for 5,000 years ago, and another one is for 2,000 years ago. But we can exactly consider it as one of them. It can be a sum of them. Yeah.
Yeah, sure. Okay. Any questions? Okay, apparently not. So thanks again, Nairi.
You're welcome.
So I don't know if Aura is here. Let me check. Nope. Okay. Bye.
Sorry, David. May I go for
Yeah,
my
yes. I mean, if you have,
yeah.
if you have a,
Yeah,
if
thank
you have a
you.
course, of course, yeah. Go ahead.
Yeah, thank you. Bye-bye.
All right. Bye bye. Okay, so we're gonna well, we're gonna switch directly to Guillaume, then to about Aura, so she will give a presentation next time. So Guillaume, so we're sharp on time actually, so it's not
perfectly. Yeah.
All right, so you can share your screen.
Yeah.
And you can start whenever you're ready.
Can you see my orange slide?
Yes, it's very orange. All right. Yes.
Yeah, very orange, yes, indeed.
Yeah.
Okay, so thank you for proposing to talk a little bit about PSHA. First, I would like first to apologize in advance because it's very possible that many things I say today have already been mentioned and well explained by previous speakers in the past months. But as it is a lecture context, it's often say that it's very important to repeat to be sure that the concepts are well remembered by the students. So let's repeat once again, but this time I will try to change a little bit the focus, and I will talk in particular about seismic source model and the building up of seismic source model for PSHA. So in a way, I'm looking the PSHA framework from the modeler's point of view. Okay, so wait, pass. Okay, so I will just rapidly remind you about the general principles of PSHA. And then we will focus on the seismic source models and the key components of this model. I hope to have some time to discuss a little bit about the propagation of uncertainties, and before concluding, I will stay relatively high level because I will talk about many topics we could discuss about for probably hours. So, okay, just in order to cover and to give you an overview of all the questions that can be raised when you're building a model for PSHA, I will stay relatively general, but giving you references so that you can investigate further if you want more details. Okay, so the general, okay, sorry if I don't see all my slides. Okay, that's better. The general principles of PSHA that we are aiming at quantifying the probability that a given intensity measure exceeds a specific value at a target site and over a given period. So the framework is often described using this simplified equation, which is actually the formula for a hazard curve. And this formula describes the probability of exceeding a level of intensity or acceleration x, for example, over a given period. So you have an equation that is composed of several terms. And I have color-coded the terms as a function of which part of the model they refer to. So you have in green the components related to the seismic source model, related to the description of seismic sources, their strengths, and so on. And you have in orange the part related to the ground motion model. So with the PSHA, the idea is that you span a collection of potential seismic sources with this sigma term here, sources I, sorry. And for each source, you compute a probability based on the scenarios for source distance and magnitude. And you combine the occurrence of a specific scenario in terms of magnitude and distance to your site with a ground motion model, or the probability that the acceleration of recorded for this scenario at a distance r exceed that level x that you are investigating. Just to mention, intensity measures can be of different sorts. So we often refer to peak ground acceleration, PGA, but many others can be used for different purposes. You have PGV, peak ground velocity. You have also spectral accelerations for specific periods, but you can imagine other quantities as well, depending on your interest. So the outcome of the PSHA is the hazard curve.
Guillaume, just a quick question. What is VI exactly?
Okay, this is the rate. This is the rate.
All right, okay.
The rate, the seismicity rate, the activity rate of each source.
Okay. Right. Okay, thanks.
I will give more details on that later. So the outcome is a hazard curve, the typical outcome. So this curve is actually obtained by applying the previous equation. And for each acceleration level x, you have a value that is given by the acceleration, the formula, sorry, in the previous slide. Okay, so these hazard curve can be expressed in terms of annual rate of exceedance, as it is shown on this example, which comes from this formula, but it can also be expressed in terms of probability of exceedance, return period, annual probability of exceedance. So this is why sometimes the hazard curves you see on the graph have different shapes and also have different magnitudes as well. It's important that you keep in mind that when you are looking at working with hazard curve, the target seismic hazard levels that you consider depends on the context, actually. For example, if you are working with the building of a normal housing, you will look for shorter return period, so corresponding to lower acceleration level, lower intensity measure levels. but the more critical you go with your infrastructure, and the longer the return period, and so consequently the higher the spectral acceleration actually. So for example, for nuclear power plant, we often consider a 10,000-year return period here. So you see that correspondingly the acceleration levels considered are much higher than those considered for normal buildings. So who use this kind of information? So there are many people using this kind of hazard curves. One typical use is for earthquake engineering purposes. So the hazard levels and the acceleration levels that you obtain for specific frequencies or periods will be used as an input for to study the dynamic response of buildings. So this dynamic response can be modeled in different ways, from the very simplified stick models for buildings to the much more refined three-dimensional modeling of the building response. Just to be short on this complicated slide, there is also there is also the performance-based earthquake engineering approach, and this kind of data, hazard curves, can also be used to improve the traditional earthquake design techniques by introducing performance objective, and you can try to combine to use this information from the hazard curve to evaluate the probability to exceed specific engineering demand parameters, like, for example, the inter-story drift. And this gives you a hint on the damage that you can expect for specific buildings. And you can estimate some loss function that you will try to optimize when you design your building. So you can build buildings that are resistant to specific loading. So this is related actually to the use of this hazard information for seismic risk. So I'm just reminding here for information the risk formula, the risk equation, where the probability of failure here depends on what we can generally call a fragility model, and the hazard curve. So the hazard curve we had before is directly used here as an input for the calculation of the probability of failure. So in the nuclear industry, the probabilistic risk assessment is used for specific component, but can also be used at the system scale, where you combine hazard curves and fragility curve associated with specific systems in logic trees that can be very complex, to identify potential failure scenario leading to spore damage frequency, so a kind of nuclear accident, for example. And you can, in the end, compute the probability that such an accident could occur. And you have to prove that your plant, for example, is able to resist such is characterized by a probability that is sufficiently low, typically 10 to the -6, 10 to the -7. So we have to prove that our facilities have a very, very low probability of failure using this framework. Another typical outcome of PSHA is the construction of hazard maps. So hazard maps are often represented as colored maps, where the color itself is related to the value of an acceleration level. Here it is for PGA, in this example for USA. It is the PGA level for a period of 2,475 years for the collection of sites that cover the whole US. this kind of hazard map are typically used or considered by regulators when they want to set up regulation on the building rules, for example. Okay, so all these slides were just a reminder of what is PSHA and who is using actually the outputs of PSHA. I will now consider the seismic source model in particular. So I come back to my formula. So now you're very used with this formula. You have seen it once already, and you recognize the colors. So until the end of this presentation, we will only consider the green part. So I will not talk about the ground motion model. It can be maybe it can be a good idea to have a future lecture on ground motion models, but for today we'll focus on the green component, so the seismic source model. And the seismic source models has three terms. So you loop on every sources. So you imagine you have n small s seismic sources. For each source, you will need to use or you need to characterize your source with these three ingredients. First, a stationary rate, ui. Second, frequency magnitude distribution. And third, a spatial distribution of seismic sources. So this is the outline we will follow in the next slide. We will follow these three components one by one, and we will discuss on the modeler's perspective on how to set up values for these three quantities for PSHA. The general workflow when defining seismic source models is maybe first to start with the spatial distribution of seismic sources. And this is elaborated based on the multiple types of information from geological settings and varying geophysical information. Then for each source, the modeler has to define specific seismicity parameters that are based mainly on the seismological information contained in earthquake catalogs and also given by our knowledge on seismic faults. Once all sources are well characterized, then there is also the question of how to combine all this representation of sources in a single model. And for this purpose, we can combine different modeling approaches in a logic tree, for example. Okay, so let's now focus on the first ingredient for our source model, the spatial distribution of source. So the classical example, the classical approach, the one proposed by Cornell at the beginning, actually, is to model seismic sources as area sources. So these areas are supposed to have an homogeneous seismic activity all within the area, and also are also described by homogeneous seismotectonic properties. So this includes actually also a type of focal mechanism and different geological or tectonic settings. So these areas are typically defined from a collection of geological and geophysical observations. So there is no specific rule, but you can define your areas based on the gravity fields, on the stress field orientation as well, on the fault orientation, fault density, seismicity, obviously. But all of this to actually highlight that there is really some significant variability in the zoning schemes. You have an example on the right-hand side where for the same area, it is Southeast France, we have 4 alternative area source description. So I cannot tell for this example what were the motivations for drawing area source for one or the other scenario. This is an example where the model has 4 alternative, where we have 4 alternative area source models. And the color of each area actually corresponds to, is related to the rate of magnitude, of potential magnitude 6 earthquake in each area. So you can see that can lead this variability to significant variability in the seismic activity rates at target site. If you consider, for example, these 2 target sites, the triangles, you see that the seismic activity at each site depends a lot on the zoning scheme. So in itself, it constitutes what we call a source of epistemic uncertainty. And we try to come back on this later, but the general idea is that it's very hard to say whether the first one or the second one is the true for our modeling. It's rather that these are several options, several possible options, and we prefer considering all of them to be sure to cover the whole space of possible area source models. So yeah, so this type of partitioning also in the end depends also significantly on expert judgment. Another type of spatial distribution often used with PSHA is the zoneless models. So zoneless models actually it more or less the opposite of the area source, as it consists in a continuous and actually quite smooth description of the seismic activity over a region. So you have an example here of the first zoneless model proposed in the literature in '95 by Frankel. And you have a continuous description of the seismicity rates, but you cannot really see sharp transition between specific areas. You have a continuous field. And actually, it's good to keep in mind that the resolution of this zoneless model should reflect the spatial variability of the seismic process itself. So it's good to recognize areas of high seismicity rates and areas of low seismicity rates. So the resolution should be adapted to reflect this variability. And then this resolution should also reflect our level of knowledge. That means actually take into account at least a measure of the uncertainties we have on the process and on the location. So today, the building of a zoneless model can be done using several methods. There are many. The most popular methods are kernel density estimation methods. So we use the 2D smoothing kernel. So the 2D kernel can be of any form. You can have a 2D Gaussian model, 2D Gaussian kernels of fixed width or adaptive kernels or power law kernel. But there are many families of kernels. You have different approaches based on the spatial partitioning methods, like the Delaunay triangulation, Voronoi partitioning, for example, or approaches maybe more complicated, but also worth mentioning, based on the modified likelihood approach, where you try to estimate the rates over a grid, but you constrain the spatial distribution of your rate to be smooth enough, and you can use, for example, the Laplacian penalty operator proposed in the EPRI report to force the smoothing of the seismicity rates over your grid. But from the modeler point of view, you have to keep in mind that this choice of kernel is not completely innocent. It's not innocent because it drives the smoothing, the way you spread the seismicity over your area. For illustration purposes, I have just used, I'm just presenting a use case where we smoothed the seismic activity in France using two different kernels. On the left-hand side, we are using an adaptive 2D Gaussian kernel. And on the right-hand side, you have a power law kernel with a magnitude-dependent bandwidth. So in France, the seismicity is low to moderate magnitude. So the kernel is quite sharp, actually. It's quite peaked. And so using this magnitude-dependent kernel on the right-hand side, we obtain a much more fine-grained or granular representation of the seismicity rate compared to the adaptive approach, which smooths much more the activity. In the end, you obtain maps with a total seismicity rate over the area that is equal, but locally you may have significant variations. So this can also have an impact on your target site. The third option we have to describe the location of our seismic source is to use faults, to describe the sources as a faults or as systems of faults. So you have on the right-hand side a nice illustration from the USGS with the USERF3 model for California, where you have a collection of faults with specific parameters detailing their properties. So, but if you want to go for this kind of representation, it actually requires an appropriate knowledge of many things like the geometry, the slip rates. It requires also to have an idea of the past and the paleo and the recent seismic activity to be able to construct your sources completely. You should also be aware of the uncertainties related to these quantities. And this is not obvious because sometimes we have, for example, estimates of slip rates, but we do not often have uncertainties on slip rates, for example. So this is why also this representation is not easy for for low to moderate seismicity countries, such as France, for example. Because maybe if we know where our faults are, we also maybe for some faults or for most of them lack knowledge on the slip rates. So this is an issue we need to tackle actually when we have to deal with this kind of model for low seismicity area. In addition, there is also the matter of background activity because to consider because these faults can help at describing seismicity occurrence along these faults, but you have also in your model to consider the possibility that the earthquake occurs on a non faults or in a neighboring area, but not on the fault itself. So you have to combine actually in the end your faults with some either some area source underlying area source model or underlying zoneless model to model or to represent the background activity. And the way you do that is not fine. You have to be careful not to count hazard twice. You need to really to consider how you can combine these two types of representations to produce one single model. I would like also to mention rapidly the approach of Thomas Chartier and Una for the characterization of seismicity parameters for faults. I think today, if we want to add faults in a PSHA model, it's a very interesting approach they propose. Considering fault segments at the system scale. And their approach actually permits to estimate seismicity parameters for each fault segment by treating the rupture occurrence at the system scale and considering different scenarios for a given fault system, considering that rupture can rupture one single segment, or it can also rupture several segments. So if you can characterize the magnitude frequency distribution at the scale of the fault system, and if you know also the slip rate budgets for each of your segments, their approach permit to recover or estimate the magnitude frequency distributions for each segment. And this is typically the kind of information we are looking for, because for each fault segment we will put in our model, we will need, and this is what we will see later, we will need to associate each segment with a frequency magnitude distribution. And so this is a very interesting perspective. For example, you have here in the paper a typical use case of 3 faults, F1 to 3, that can combine as a single rupture or combine 2 by 2 or all 3 together. And you know the total frequency magnitude distribution based on your catalog. I will come back to that later. And so using their approach, they were able, in this example, to reconstruct the frequency magnitude distributions for all segments. And you see that for the single rupture, you have a larger proportion of small magnitude events, but for fault rupture, for rupture that break 2 or more segments, they are associated with larger earthquakes, actually. So it's a very interesting approach to consider when you want to characterize your segments. I'm sorry to be so fast because it would require much more time to explain in detail, but maybe if it gives you the will to read the paper, I would be already very happy. Okay, so we've talked about the spatial distribution at the surface, actually, but there is also the matter of depth. When you're building your model, you need to give a hint on the distribution of hypocenters. And because these distributions affect the ground motion recorded at the surface. So it's an important parameter. And also, when you have an earthquake, we know that this earthquake will occur at depths. What we don't know, it is the value of this depth. So if we state the problem this way, maybe it can help understanding that this is actually an aleatory uncertainty. So again, I will come back to this difference between aleatory and epistemic uncertainties later, but okay, so this is considered slightly differently in the calculation. But the fact actually is that hypocentral depths are also very poorly constrained in earthquake catalogs, and especially for historical events. Because when we are doing PSHA, we consider seismicity over a long term, and sometimes we have to consider earthquakes that occurred 200, 400, 500 years ago, for which the knowledge is very poor. And however, actually, as I said, the catalog is our unique source information. So we have to make the most of it. So here is one example from Visini and co-authors. For Italy, they considered a specific area in Italy, and this is just an illustration, actually, where they mapped the distribution of hypocentral depths and discussed in their manuscript whether using a unimodal distribution for depth is better than using a bimodal distribution. So this is, I don't want to discuss about this particular fact in detail, but well, in this case, and for the larger earthquake in their database, they found that the unimodal was a good description. And actually what I find interesting in this picture is that they try to make the most of their catalog and to constrain these depths from the data itself. But not all catalogs have such nice distribution of hypocentral depths. Sometimes it is very picky because hypocentral depths sometimes are fixed by observatories for practical purposes, when you can have peaks at 5-kilometer depth, 10-kilometer depth, or 15, for example, because they are fixed in advance. So this is something that you will need to consider when you're trying to estimate your distributions. Okay, I will switch to another aspect, which is the rate itself, the stationary rate hypothesis. And yeah, I will just remind, I will go very rapidly on this slide, but you have to keep in mind that in the Cornell-Maguire approach, so in the PSHA approach, the rate of earthquake in each source is assumed to be stationary. So that means it can be described by a Poisson process, and this hazard curve reflects the incidence associated with the sum of independent Poisson processes. So as a consequence, the modeler must provide for each seismic source a stationary rate description from the input catalog. So that means that we have to adapt. It's not exactly representative. It's not representative of the exact reality, because we know that the seismicity rates are non-stationary. But for PSHA, we will stick with this hypothesis. And so for the modeler, one of the questions is how to make my catalog stationary. Because if I want to characterize the seismicity rate, I have to use an adapted data set. So this is the purpose of declustering methods. So we to make our catalog stationary, we will separate two different populations from our catalog. A population of background events that are events considered independent one from the others, and it's what we call main shocks, and triggered events, which include foreshock and aftershocks. Yeah, if we follow the whole paper by Gardner and Nopov, they propose the declustering techniques and that permit to remove aftershocks from the catalog, and they also explain that in doing so, the background activity that remains is stationary. And as an illustration, I have here a plot of the Japanese catalog of earthquake, which has been separated for the background part on the left-hand side and for the triggered part on the right-hand side. So you have the map view on the top, and on the bottom you have a longitude time representation. And so it's very clear when you look the bottom panels that the background events have an activity that's apparently rather stationary in time, but the triggered activity is much more formed or consists in a collection of bursts, actually. So to make your catalog stationary, we use declustering techniques. Again, as we mentioned before, several methods are available in the literature. There is the Gardner and Nopov approach with different space-time windows. There is the Riesenberg approach, which actually has a faster decay of dependent event in time. And there is the Zaliapin approach, the recent approach by Thomas Chartier as well. Okay, so there are several alternatives. And it's good to keep in mind that they are not all equal. There is not a single reply to this problem. By the way, while speaking, I'm just noticing that I forgot to mention the model and independent stochastic declustering approach proposed by David and some colleagues as well. So sorry for this missing reference. I will correct in the presentation later. But each approach actually depletes the catalog differently. So you see here 4 examples. This is an example produced by Thomas Chartier and Marco Pagani. You have an original catalog in black, and you have in red the events kept in the declustered catalog. So the more black dots you see, that means that the more aftershock you have removed from the original catalog. So you see the top panel show the results of Gardner and Nopov approach. The bottom left, the Riesenberg approach. The bottom right, the Chartier and Pagani approach. So there are clear difference in terms of number of events, in terms of magnitude frequency distributions as well. But even more, there are also impact and impact on the Poissonian character itself of the final catalog. So in their study, Thomas Chartier and Marco Pagani propose to score the Poissonian character of the declustered catalog. I won't go into these details, but you can read their report. It's very interesting. But what we can see is that from one method, okay, the different methods are colored dots here. You see that from one method to the other, the Poissonian score, which is 0.5 for synthetic Poissonian catalog. So the Poissonian score is not constant actually. So they are not producing exactly a Poissonian catalog. And some methods are worse than others, and it also depends on the original catalog. So this is something to consider, because in the end, this has an influence on the hazard curve. You have here, for this example, same example from the same paper, the impact of changing the declustering methods on the final calculation of hazard curve, all other things staying equal. So you see that you can have a significant variation of the final probability of exceedance depending on this choice. Let's now talk more about the frequency magnitude distribution itself. Actually, we already talked quite a bit about this distribution, but there is maybe a little bit more to discuss. So with the spatial component, this is the other key component of the seismic source model. It characterizes the seismicity rates, so the A value, and it also governs the relative proportion of large versus small earthquakes. So again, you can characterize your distribution using different families of models. There is the characteristic model, sometimes used, and there is the well-known Gutenberg-Richter model. So this is one of the important assignment of the modeler to estimate the frequency magnitude distribution parameters for each source. So I will review rapidly. There is the characteristic model, the first I mentioned about. The characteristic models is a power law decay of the number of earthquakes with the increasing magnitude for small earthquake. And then this model favors a specific magnitude value, a preferred value for a specific fault segment. So this is a model that is motivated by the need to reconcile seismological observations from catalog, which often show Gutenberg-Richter-like model. I will come later to this model. And with geological observations for specific fault segment that present a higher rate than expected for a larger earthquake. So this is one option, and but the most frequent frequency magnitude model used for PSHA is the truncated Gutenberg-Richter model. So this model is a power law description of the the number of events as a function of magnitude, and truncated because there are actually one upper magnitude truncation, M max, which is a threshold which denotes the upper bound above which an earthquake is impossible. So this is a parameter that you will have to estimate, and this is an important one. And note also that there is also another important parameter, which is mean, which is a lower bound truncation of this model, which denote the threshold below which the information in the catalog is incomplete. So you cannot really fit your model because the data is incomplete. So the modeler has to deal with these two aspects: characterize the completeness of his catalog and estimate the maximum magnitude for each area source. I will go very rapidly, but what kind of completeness problem can we have with PSHA? So here is an illustration. You have here the historical catalog for France, spanning the period from 1200 to present. And you see that the number of events has a density that the density of events, decrease for historical periods. So we have estimated for this catalog a completeness threshold that is represented by this dashed red line. So you clearly see that you have very different periods. Here you have the beginning of the instrumental period with the detection of lower magnitude events. And you have also an historical period, which is characterized by much higher completeness levels. And the key problem is that actually this completeness evolves in time. So it's not a constant feature. And the other problem is that this completeness also varies spatially. And for example, you can easily anticipate that if your catalog of historical earthquake is based on the written manuscripts or written reports produced during the historical period in old manuscripts and so on, you have richer information in a densely populated area compared to mountain area or countryside for historical times. So this is something we need to consider also. So we have to characterize the completeness in space and in time. I'm already long, so we'll continue rapidly. For the maximum magnitude, we have to decide for each source what is the adapted upper bound beyond which an earthquake cannot occur. And for this purpose, there are several approaches, several possibilities, or maybe you can combine them actually. If you are lucky enough to have a good knowledge of the geometry of your fault and if you know well how fault system how rupture can behave in your fault systems, you can geometrically assess what is the maximum magnitude in your system. But if you're not able to do so, you have to use the different approaches. So there are approaches that use a Bayesian framework, and they use a prior for your source, where your prior defines a maximum magnitude based on similar tectonic context all over the world, and the likelihood function is constructed based on the statistics of extremes. So in the end, you can obtain this kind of distributions. So you have a prior, for example, which is the smooth dotted line distribution, and you can obtain using such approach a posterior distribution for your Mmax. That is, for example, illustrated in this example by the thick green line. So in the end, you obtain a distribution for Nmax. And again, you don't know what is the true value. You know that it can be one or the other. So this contributes to epistemic uncertainties. I have mentioned several times during this presentation the word uncertainty. And there are two kinds of uncertainty that are considered in PSHA. One is what we call epistemic uncertainty. And this family of uncertainty are related to our current knowledge of the seismic process. So we hope that this data one day can be reduced by data acquisition, by doing research. If we increase our knowledge of the process. So this type of uncertainty is viewed as an alternative scenario, and it is implemented in the calculation in logic trees, where each branch represents a technically defensible interpretation of the seismic source model. And there is another uncertainty, which is the aleatory uncertainty, which is intrinsic to the seismic process itself. For example, as I said before, you know that your earthquake will occur at depth, but you never know which depth it will be. Even if you know that you have an area where the seismicity is shallow, for example, you cannot know today. You cannot know if it will be 3 kilometer. If the epicenter will be 3 kilometer depth, 1 kilometer depth, 5 kilometer depth. So this is really quantity. This is a random variable. This is a quantity that needs to be distributed. So this type of uncertainty cannot be reduced and has to be implemented by the integration of the distribution in the calculation. So it's described by a distribution and not by a logic tree. Here is an example of a simplified logic tree for PSHA. So you have, so this is a complete PSHA logic tree. I mean, because it gathers branches for sources, but also for ground motion. And the logic tree for sources, for example, propose three alternative models. One is the area source models with four alternative zonation. Another is the fault-based model, and another alternative is the zoneless model with different types of kernels. Then you have also to combine all of these branches with a branch on the maximum magnitude for each zone. And then there is also the epistemic uncertainty on the ground motion itself, but this is not really our topic today. The important thing here is that you have weights associated to your branches, and these are the red number. For each level, all your weights sum to 1. And you have to put weight. So you have to weight which of the scenario is more likely than another. And actually, this is something that is often done by expert judgment. But I just wanted to mention rapidly that there are also recurrent discussion on the approaches to weight, to adapt this weight based on observations. You have, for example, the possibility to rank your different branches based on the comparison between the mean expectation from a model based on the generation of synthetics, for example, and observation. So this can be treated in a Bayesian framework where you can try to update the weight of your branches based on how each branch agree with some observations. It can be ground motion observations, it can be a catalog, it depends on your problem, it depends how you want to state it. In this example, there is a study by Ilaria Mosca on the UK, and they had collections of many zoning for their source model, and they actually generated synthetic catalogs for each area source. They combine these catalogs and they finally compare with the true catalog to weight their branches. Okay, I have two slides before my conclusion. I wanted to just give a word about the calculation of hazard curve itself. So this goes beyond the seismic source modeling because it includes the ground motion model. But I just wanted to mention that what I have talked about is the classical approach, what we call Cornell-Maguire approach, where the computation of hazard curve rely on the numerical integration of the probability of exceedance. So you have this probability of exceedance that I mentioned several times today. And the classical approach consists in the numerical integration of this big integral to obtain your hazard curve. But there is another way to do so, which is what we call the event-based approach. So the general idea is that, as I just mentioned before, from your model, you can generate synthetic catalogs of earthquakes. These catalogs of earthquake can be combined with some ground motion models that give the probability that a specific magnitude and distance scenario produce a given acceleration. And so if you do many simulations using a Monte Carlo process, you can reconstruct empirically your hazard curve. So this is another way to obtain your hazard curve. And for an infinite number of simulations, you converge to the classical approach. The results converge to the classical approach. So there are some pros and cons of this approach, but among the pros, it's worth mentioning that this can help adapting to different seismicity model. And actually, this can be a way to include non-Poissonian seismicity in your PSHA. It presents also a very flexible way to handle uncertainties, in particular correlated uncertainties between random variables, because there are many quantities that are probably correlated, and it's not easily integrable in the classical approach. Okay, and it has other advantage like it can adapt easily to risk calculation, and it permits to identify rapidly the earthquake that cause to identify directly the earthquake that caused the largest ground motion. Among the inconvenience, we have the fact that as it's a Monte Carlo process, there is a non-unicity of the results. And also that it is probably the main drawback is that it is very computationally expensive, but it's also very flexible. So this is why I wanted to mention it also. So I will now conclude. So maybe my take-home message is quite simple. And I just wanted to remind that the PSHA framework actually accounts for a fully probabilistic description of seismic source parameter. And I want to stress today that the modeler's assignment actually consists in accounting correctly for all sources of uncertainty, so including the spatial distribution of earthquake and the selection of the right topologies, the earthquake recurrence patterns, and also to separate correctly aleatory and epistemic uncertainties. And for the modeler, actually, it's very important to keep in mind actually the limitation and the underlying hypothesis of input data set and also of the methods you will use for the characterization of sources. And this is why today I've chosen to present this aspect of building a model by presenting a variety of methods, just avoiding to make think that there is only one way to do. There is an expression we sometimes use that successful source model shall cover the center, body, and range of all technically defensible interpretations. So this is a statement that is often produced in IAEA technical reports, but I think it's also a good summary of what we should aim when we build a source model. There are many topics about which I have no time to talk today. But there are also interesting perspectives for further work on PSHA. Among these is the topic of non-stationary PSHA. There have been many work in the past that I think needs to be investigated further because it is an important aspect to consider. There is the topic of also vector-valued PSHA, where actually the idea is to compute not only a single hazard curve, but a multidimensional hazard curve in order to include the correlations between intensity measure. For example, the correlations between accelerations at different periods. And this kind of framework also permit to do other things, other actually unexpected things like accounting for aftershock related ground motion in a PSHA study. And to conclude, I just want to mention that this probabilistic framework is not only used for seismic hazard assessment, but has also been used, has also inspired many other types of hazard assessment. And recently, the scope, at least in the nuclear industry, the focus has turned to another type of assessment, which is the probabilistic fault displacement hazard assessment. But this is another topic that maybe we will have nice presentations by other partners of the project in the next months, I hope. So that's all for me, and I will stop here with my nice picture. Thank you for your attention.
Excellent, Guillaume. So very clear presentation. Thanks a lot. So there is time for questions. I can ask several, but I wouldn't mind the students to ask instead of me, if possible. So anybody?
Maybe it was fast.
Well, I mean, you covered a lot, but I mean, everything was relatively clear. And as you mentioned, I mean, several aspects were already covered by previous lectures. So at this stage, you're not. I mean, people are aware of how that works. So anybody? Well, I can start, and then we'll see. Because I was wondering about, I mean, the special components. So first of all, you didn't mention using strain rates. So I was wondering, like, if that's coming into the equation as well.
Yes, I can reply.
Yeah.
Yes, it's coming into the equation. Actually, it's coming, and yes, it can help. It can help in many directions, actually. It can help at estimating your slip rates, for example, when you are dealing with faults. It can be useful. And but there are many applications we can imagine. And I have in mind a proposal by David Beaumont in the past years that was to use the slip rate to remove the branches in your model that predict that overestimate the slip rate. To use the slip rate as an observation for Bayesian updating, actually. And if you have a Gutenberg-Richter distributions for each branch, so you can estimate what would be the expected strain rate in your source, and you can compare with what you observed today with all the limitation that it that you can imagine also, but it can be used in this
Because at some stage you show for
evolution.
France, I mean, you showed two different, smoothing by two different kernels, and one was from Céline, I believe. It looks like so. If I'm correct, what you said is that Céline Beauval used a kernel that is power low with a cutoff that should correspond to the rupture length of the earthquake. Is that right? So it gave a map with fine details, but then it's really depending a lot on your previous data. I've always been wondering, whether you overfit or not, and using strain rates normally, allows you to remove some of this overfitting. I don't know if you agree with this.
Not sure to get what you call overfitting in this example, but
Well, I mean, it's very fine
it's
details.
fine grained. It's too much fine grained. Yeah, too much
Yeah,
details.
and you basically expect, the future earthquakes to occur exactly like the previous ones.
Exactly.
So there
This
is
is the point.
no uncertainty on, so you have a perfect knowledge already. So that's, I mean, to me, it's overfitting,
Yeah, I see. I see. Yes. Yeah, there is something probably probably slip rates can be an ID. Yeah, to
Sleep rate
another
or,
ID can be to propagate location uncertainties, but I'm not sure it will help a lot because it will only. Yeah, I'm not sure it will help a lot.
Mm.
No, I don't know. By the way, I just mentioned that this is a smoothing that I did myself using the parameters of our paper. So maybe it's not exactly what Céline had. It's possible that I just
All right, okay.
misinterpreted what she did before. So I do not pretend it's Céline's result.
Okay. Questions, anybody? Okay. Well, I can ask others. I mean, just feel free to interrupt me, guys, if you want to ask a question, because, well, I won't ask too many in any case, but still, is it, talking about declustering, so, well, I'm going to ask you the question I'm asking all the time, is I still don't understand why you need to decluster,
I
because
missed
the aftershocks do contribute. So I understand it makes for simpler, predictions because you suppose it's stationary rate, but then there are ways to, have a full distribution of rates instead of having only one. So as you mentioned, so I don't know. So maybe Una can say something as well. I don't know, but and it's still, I mean, it seems to me that using stationary rate is such, a gross approximation that I still don't understand why, people do this.
So sorry, the connection was a little bit interrupted. You asked why we use a constant rate actually and not a
Yeah,
distributed
because
rate.
yeah,
Indeed, that's a very good idea. Actually, this is what we do that. Actually, we do that because um, I'm just wondering whether it's aleatory or or epistemic. I'm not sure. It's maybe more epistemic in the way we do today. But we actually we include uncertainties on A and B parameters. For example, if you consider Gutenberg-Richter, we include the uncertainties on A and B. So
yeah, but it's more than just the the uncertainty on the estimated A value, like, so it's due to the fact that that the natural variability is much
okay,
higher than just computing one rate.
yes, and so it can be modeled probably by
Yeah.
declustering several times using stochastic declustering, generating a new catalog, for example, each time.
Yeah, I mean, there are theoretical approaches like, using, Kagan, did a bit of work on this, with the negative binomial, approach and things like that. So just to predict, a full distribution of rate instead of having just one value in the end.
Mm. Yeah.
you know, so.
But we propagate actually. It's not exactly as I said. We propagate at least on
Yeah,
decimation.
yeah, but I
At least
think
on
it's
decimation. Yeah, I understand.
okay, but it's possibly under, you know,
Yeah, estimated.
you know, I mean, the variability is underestimated. Yeah.
Yeah.
So I'm going to stop with my questions because I mean it's very interesting. But okay, so anybody else or comments or whatever?
Probably I have one. Can you hear me?
Yes, yes,
Yes, we can hear you.
Yeah.
Sean.
Okay. So if we have several models, I don't know, such as or different kernels, what will be the weight for each of them? How can we attribute the weight for one kernel or the others?
Yes, but this is the big question actually.
If we use like the method like the one from Celine, what will be the weight in our logic tree, and what will be the weight for the one of Frankel?
This is there is not a single response because but first you can gather a meeting of 20 experts and you ask them to their preference, and this is how it is done in what they call SHAC. You know,
Yeah,
SHAC.
We've lost you, Guillaume. I don't know if you can hear.
So what they prefer, what do you have confidence in also?
Right.
And then you can try to weight more objectively based on your observations. And this is what I mentioned in the end. But again, this is not the perfect solution as well, because then the choice will depend a lot on the data you use for comparison. And you have to be cautious of the representativeness of your data set. So you have to include probably all the uncertainties also, but and the variability of your data. But no, there is not a single reply, Jarod. If I have a kernel and area source, yeah, you have to discuss. Today it is done by expert judgment and based on what you trust more. I tend to trust more zoneless model because they fit seismicity. They are more closely related to the spatial distribution of seismicity. But it's also related to a short-term image of seismicity. So the seismic process, especially in low seismicity areas, spans over longer timescale than the records we have. So it's only a snapshot. Maybe you have to include information, the geological information. This is an interesting point, but it's not easy to get. Yeah.
Okay, thank you.
If you read papers on PSHA, you will see many studies where they give their weight and they try to explain why they weighted this way or another. You have, yeah, depends. There is not
Very empirical.
no.
Yeah. Okay. Anybody else? Okay, so maybe we can call it today and thank again Guillaume for putting up a very nice presentation. Thanks a lot, Guillaume.
Thank you for attending.
Yeah.
Thank you.
Thank you.
Yeah, thank you.
Have a good day.
Okay, and bye bye everybody then.
Bye-bye.
Bye.